Good morning, everyone. Martin Fair here from SLCan. I'm very pleased to welcome you again to our ongoing webinar series. I'd like to thank you today for joining us for the webinar presentation of monitoring air quality of indoor environments. I'm pleased to introduce Sandra Tedesco, who is currently the Sustainability Consultant at RWDI in Toronto. Sandra specializes in high-performance buildings that promote occupant health and environmental sustainability. She has international research and consulting experience in this area and brings this multidimensional perspective to all roles. She's previously been involved in academic research that examined the impacts of building design and operation on indoor environments and occupant health, and is now applying these findings to projects through her current role as sustainability consultant. Sandra has and continues to be involved with developing and delivering education through the University of Toronto, the Canadian Green Building Council, and the IWBI. She's currently serving as a WELL Air and Thermal Comfort Advisor to help shape the next version of the WELL Building Standard. Just a reminder before I turn it over to Sandra that if anyone has any questions throughout the presentation, please feel free to type them in, and at the end of the presentation we'll make sure that we go over all the questions. Without any further ado, Sandra, I'll turn it over to you.
Great, thanks, Martin. Good afternoon, everyone. I see it's officially noon. So thanks for joining me over your lunch hour. Today, we're going to talk about monitoring air quality of indoor environments with a specific focus on laboratory environments. Just to frame today's discussion in a little more detail, we have four main topics that we're going to discuss. The first is a general introduction to indoor air quality. So this is really the motivation for why we should care about indoor air quality in design and operation, and also some basic fundamentals, as I find it's kind of newer to the sustainability and high performance building industry as opposed to things like energy efficiency. The second major topic is design and operation strategies that we can implement to improve indoor air quality. The third is emerging frameworks in the sustainable building industry. So this is things that focus on indoor air quality and indoor environmental quality, as opposed to things like LEED, if you're more familiar. Sorry if you had any background noise just there. We had a conversation that's now ended, so hopefully it'll be more clear. And then the final topic is case studies. So now we're going to focus on some high performance lab projects that we've worked on here at RWDI, and then also showcase some non-RWDI projects that are still kind of really leading in indoor air quality and health and wellness in the lab space. And then the learning objectives that we have are to understand the fundamentals of air quality in buildings, understand the recommended exposure limits for different indoor air pollutants, understand lab-specific indoor air quality and health considerations, and then understanding different monitoring techniques and methods to assess indoor air quality in your space. So even if you don't work in a lab, a lot of what we're talking about today applies to your building type, and I hope this will be informative and possibly new. I know so far when I've been speaking to different groups, indoor air quality is still kind of a new space, and so it's quite exciting that growing attention is being put towards this topic. So to start with section 1, we have our introduction to indoor air quality. And as I mentioned, I always like to start with a motivation. Why should we care about designing for this topic? So to date, a lot of focus has been put towards climate change, and that's particularly been mitigating against climate change. So you can think of kind of the green buildings movement and how that came about and the emergence of LEED and similar rating systems here in Toronto. I know we have the Toronto Green Standard, and the focus of all of these initiatives is really to reduce carbon, reduce energy consumption in buildings, and reduce the negative impact on the natural environment. But growing evidence has already shown that the climate has changed. So while we are still working to mitigate against additional climate change, we now also have to adapt to our changing climate. So I don't know where everyone's calling in from, but I'm sure everyone's experienced more extreme weather conditions. You'll often hear people refer to shocks and stressors. So stressors, you can think of something like here in Toronto, I'll use where I'm located as an example. We're seeing increased cooling requirements in the summer, so increased temperatures and extended heat waves. So this is a stressor, and then a shock is something more impactful. So like these extreme rainfall events we're seeing where we're getting basement floods, those types of things. So buildings now not only have to mitigate against climate change, but they have to adapt to our changing climate and be able to withstand these new weather events. But if we just focus on mitigating and adapting to climate change, you could end up, if you were to design to optimize both of these, you could end up with, I'm an engineer, so I can say this, what people often make fun of engineers as having the, traditional windowless box. But we have to consider a third element of sustainability. And that's the occupants. That's enhancing the occupant experience in a building. And then we now see this next wave, kind of the healthy buildings movement. If you're familiar with WELL and FitWell, you can see that this is gaining attention, still very much in the early days compared to green buildings and resilient buildings, but it's becoming a very important third pillar of sustainability that growing attention is really being devoted towards. And this is really good to see because there's often been a misconception about air quality, particularly when we're comparing indoor air quality to outdoor air quality. So this is something I grabbed off Twitter from someone I follow. And it says the chairman of EPA's Science Advisory Board says federal regulations on ozone are unnecessary because most people spend more than 90% of their time indoors. So that's the funny thing. Most people do spend 90% of their time indoors. And in any type of building, that time you spend indoors means that you're exposed to a number of different indoor air pollutants and potentially harmful components of that space. So we have chemical reactions from different materials and cleaning products. We have bacteria from humans, fungi from plants, or things that are brought in from the outside, like on the bottom of your shoes. We have emissions from different material products, indoor combustion. Things like occupant activities. Cooking is a big cause of indoor air pollution. Even walking across a room can cause particle resuspension. And there are just a number of other things that cause us to be exposed to different indoor pollutants indoors. And what's interesting is that these levels of these indoor pollutants are often 2 to 5 times higher than the concentration we would find outdoors. And then when we factor in this statistic that, the average North American spends about 90% of their time indoors, when you factor that time into the equation, your dose and therefore your health is largely governed by the time you're spent indoors and the different exposures you're experiencing there. So you might be wondering, okay, well, everyone's like cooking, everyone's walking, everyone's vacuuming. What kind of effect does this really have on my health? And that's one of the big drivers for designing for indoor air quality. I don't know if anyone's seen this study. I've noticed it's been kind of flying around in presentations a lot more lately. But this was done out of the Harvard School of Public Health. And I like it because it provides a more quantitative assessment of the impact on occupant physiological and cognitive performance under different design scenarios. So basically what these researchers did is they took an office building and they simulated different environmental conditions. So you can see we have a conventional scenario that's shown in gray, and that's the leftmost bar here for each of these cognitive domains. And so in the conventional scenario, you can think of this as a building where no special attention has been put towards enhancing indoor air quality. So you have conventional carbon dioxide levels and conventional volatile organic compound levels. So volatile organic compounds come from things like materials, cleaning products, even humans, plants, this type of thing. So no special attention to either under the conventional scenario. And then under the green scenario, this is where they simulated a low concentration of volatile organic compounds. So think maybe some special attention has been put towards material selection, for example. And then in the green plus scenario, this is the rightmost green bar with the little dots there. This is where they simulated both a low volatile organic compound concentration, but also a low carbon dioxide concentration. So think enhanced ventilation there for that lowered CO2 concentration. And then they took the subjects that were in the building, so the people working there, and they evaluated their cognitive performance across multiple domains. You can see there's different categories like basic activity level, applied activity level, task orientation, crisis response, information usage, etc. And what you can see is that in every cognitive domain, the score from these performance tests increased when going from the conventional scenario to the enhanced green plus scenario. And that's consistent across the board. So the study demonstrates that design attention to indoor air quality and improving this most likely results in increased cognitive performance. And that's really enticing to a lot of people when they're designing workplace environments and they want their staff to be working at a higher level and being more productive. But it's particularly important for a lab space as well, where you really want to minimize accidents and ensure people are focused. I know when I was in academic research, I mean, you really don't want to be mislabeling samples and putting them in the wrong place or not following protocol. So anything that will help you perform optimally is I think quite worth it when it comes to the design. And then when it comes to the operating expenditure of buildings, people are often really focused on energy, and I understand. I mean, it's very important with respect to climate change, and you also have a more tangible return on investment. But when we look at the amount of money annually that's spent on a typical building, you can see there's quite a difference between the estimated annual energy costs on the right, that's 1.8 million, and then this is compared to the estimated annual salaries for people in the building, estimated around $200 million a year. And this was for a large medical research tower, so not technically a lab, but very similar in kind of the activities and people that would be working there. So you can see that we're spending all this attention to really drive down energy consumption, but there's this whole pool of money from a business perspective that's being put towards the occupants and the employees in the space that you really want to be getting the most out of. There are some studies, I will say, that try to quantify like a financial return on investment, but it's not the easiest to do, and it's there's often like kind of intermediate proxies used to determine this. So I would just caution you if you do see any of those harder numbers. So hopefully now we're kind of understanding why indoor air quality is important. It's primarily about improving health outcomes, improving productivity and performance, and from a financial perspective, getting the highest return, not necessarily financially, but productivity from your investment on employee salaries. And so now, just to kind of set the groundwork a little more for some of the things we'll be talking about later, I want to just start with a brief introduction to kind of the fundamentals of indoor air quality. So to begin, we have different types of indoor pollutants in the built environment. Typically, these are categorized as either gas phase or particle pollutants. The gas phase pollutants can be further broken down into inorganic gases and gases. So you can see under inorganic gases, we have various combustion byproducts and other gases like ozone, ammonia, radon, etc. And then for organic gases, these are things like those volatile organic compounds I was mentioning, things from like building materials, off-gassing of those materials, like office equipment, whiteboard markers, humans, hygiene products, anything with a fragrance, this type of thing. Volatile organic compounds are ubiquitous in the indoor environment, so you will likely find them in most consumer products you see in a typical building. We also have aldehydes and semi-volatile organic compounds, and then under the particulate matter category, we have different solid and liquid aerosols, including asbestos, and then we also have different biological categories, so viruses, bacteria, fungi, endotoxins, and different allergens, and then also metals. And then when we're looking at the concentration of these different pollutants in different indoor spaces, this is really simplifying things, but, and I don't mean to kind of make it seem more simple than it is, but just for the purpose of today's presentation, you can think of the concentration of any one of these indoor pollutants at any given point in time as the balance between the concentration of the sources of that pollutant over the concentration of its losses. So this image down here is showing all of the different things that are occurring in a building. I know it might seem like not much is going around when you look around, but really there's quite a lot. There's infiltration through the envelope, and you can get secondary reactions through the envelope depending on the different materials that are in there as the outside air passes through. You might introduce different pollutants into the space. You also have indoor sources, deposition, so this is things like particles settling out of the air. Then we have resuspension, as I mentioned, when an occupant is walking through the space. If you can think of Pigpen from Charlie Brown and that dust cloud around him, that's actually quite representative of what's happening when we're moving through a space. We have coagulation in the air, so different particles and compounds coagulating together, formation through things like secondary reactions, phase change, and of course the ventilation system is bringing in outside air and also exhausting air, possibly recirculating air. And then there's likely some kind of filtration component, whether it's a media filter for particles or some kind of carbon filter for other types of contaminants. And so all of this is occurring, and we can model this by taking these different factors into account and really and estimating the concentration. Sorry, SS is steady state, just saying that like any given point in time, you could estimate the concentration in the air. But the point of this is to say that pollutant levels are dynamic, so they're not going to be static over time, and they really can, like I know when I've been talking to different architecture firms about this, they're like, what, how is that possible? Why is the concentration of this increasing? And it really can go up or down, or it really depends on what's going on in that space at that point in time. And then if we want to look at different indoor limits, these are recommended exposure limits, both a short-term and a long-term. We can look at things like the NAAQS table set forth by the EPA. So they have a list of like kind of priority pollutants, and then they'll have, as I mentioned, the longer term and the shorter term exposure limits. So when you look at the time and also the concentration, you can see that for the shorter period of time, it's a higher concentration, and for the longer period of time, it's a lower concentration. When factoring those together, you don't want your dose and your exposure to be exceeded of those kind of limits set. I'm not going to get too in-depth on these. I'm just kind of letting you know that these are published, and that also the Government of Canada has some complementary guidelines. A lot of the levels are quite similar, but they do change a bit over time. And one thing I wanted to highlight is that they've moved away from kind of setting a concentration, and due to the serious health implications of fine particulate matter, or PM 2.5, you might see something like as low as possible if you're looking at different guidelines on indoor air limits, and that really is try to get it as low as possible, try to get it to zero, really wanting to minimize any potential negative health implications. So Canada takes it one step further as well, and we also have a list of target levels for different VOCs. So I think I mentioned total volatile organic compounds, or TVOCs, earlier, but there are also individual target VOCs, hundreds of these, and there are also indoor air reference levels set forth by the Government of Canada for this. So really just, we're not going to go in depth, we could talk for ages about this, but just making you aware that there are certain guidelines for health, but there are also certain guidelines for productivity in the built environment, and we're going to touch on those a bit later in section 3 with those emerging frameworks on this topic. But I just, following on the kind of the introduction to the fundamentals of indoor air quality, I do want to talk about the general design and operation strategies, because it's not just, I think oftentimes when we talk about laboratory environments, it's not just about designing to prevent kind of unsafe environments. It really is about creating work environments as well that really do optimize productivity and the research that's occurring in that space. So I don't want you to think it's all about fume hoods. It's about kind of the environment outside of the fume hoods as well. So the general approach to indoor air quality, there's a saying, dilution is not the solution to the pollution. So people use the example that like if there was something that smelled really bad in a space, like, I don't know, say someone had like a container of garbage that was just open and rotting in the sun, would you increase ventilation to try to solve the problem, or would you take the garbage out? You would probably take the garbage out. So the first priority measure in any indoor air quality application is source control. So I can take on a number of things, but I'm going to show a few examples of each later. Then after source control, we look to the next step, which is increased ventilation. So we look at different ventilation strategies to understand how we can further improve the indoor air quality. And then our third and final measure would be air cleaning. So that's like filtration or actual air cleaners in the space. And that can be complicated for other reasons, like several air cleaners actually do generate other indoor pollutants. So you do have to be quite mindful when implementing any of these strategies. But I wanted to give you a few examples. So source control, we've been talking a lot about material selection, and I noticed there's been growing attention, as I said, towards indoor environmental quality design. I've seen a lot more projects really interested in this, particularly in labs, research facilities, and healthcare facilities. And so material selection is a big one that you can pay attention to. This is an example where some researchers examined the concentration of different pollutants off-gassing from different fluorine products. So we have a conventional wood floor at the top, and then we have a green version on the bottom. And if you look at the time scale and the concentration axis, you can see that they follow, a similar pattern overall. But if we take the maximum concentration observed from the green scenario and we draw a horizontal line across the conventional scenario, you can see that the conventional scenario far exceeds the maximum concentration achieved of the green scenario. So there is merit to paying attention to material selection. I know it's not everyone's favorite job to actually chase down this documentation during the design and construction process, but if you do need kind of some additional muscle, I guess, as to why this really is important, there is measurable benefit. And as we saw earlier in that Harvard study, there is then following benefit to the occupant's cognitive performance, which is particularly important in a lab environment. Luckily, you don't have to conduct your own studies to achieve this. There's a number of material selection frameworks and kind of evaluations in place to make this type of design strategy more feasible. So you're probably familiar with declare labels, like from the Living Building Challenge. And then if you're familiar with LEED version 4, there's not only a VOC content requirement, but also a general emissions requirement. So you'll often have to accompany different materials with a test certificate to show that it did pass certain VOC requirements. Then if we look at kind of the second tier of indoor air quality design strategies, I mentioned that increased ventilation is what we'll look to next. This will, of course, depend on the type of building you have. And I know labs are particularly interesting with ventilation requirements and in fume hoods, but these types of strategies here, I grabbed these from the well building standard, and these would apply, I'd say, more to the like the work areas, the non-fume hood areas still enclosed in the lab space. So there's a number of options available. Some that are really unpopular are increasing the outdoor air supply 30% above ASHRAE 62.1. So typically that doesn't complement energy efficiency initiatives very well. And it's not the most popular strategy, but that is something that is being kind of pushed forward as a new concept in the indoor air quality and indoor environmental quality space. And then we have other strategies too that you can implement, like demand controlled ventilation, which is quite common in office buildings. But under this new feature, you get rewarded for the carbon dioxide concentration and with a reduction in the set point, say from 900 ppm to around 600 ppm, you get additional merit for kind of reducing the carbon dioxide in the space. And again, going back to that Harvard study, we saw that that does have implications for cognition in a positive direction. Then for part 3, we have displacement ventilation as another option. And I know that can be tricky based on kind of like the activities occurring in the space, like lab benches and placement of that and whatnot. And then finally, we have advanced air distribution. And this is really about supply diffuser placement to provide conditioned air more directly to the breathing zone and the individual occupant workstations. So I would say that is more complementary to the energy efficiency initiatives. Instead of just increasing the ventilation, you're paying closer attention to the actual distribution of that air. And then the final example that I mentioned is air cleaning. This really is the final step that you would look to. It really is about source control and then increased ventilation first. But one common strategy for air cleaning is to implement, say, carbon filters, or you can even have a standalone air cleaner equipped with carbon filters. And this graph is just showing the removal efficiency of different volatile organic compounds from that carbon filter. And you can see that it's achieving a fairly decent removal efficiency, kind of around the 50 to 60% range, except for formaldehyde, which is quite a bit lower. So I just want to point out that it's not effective for all target contaminants, but it is fairly effective for several. And then to complement these more general design and operation strategies, I want to discuss some of the emerging standards and frameworks. I know I was speaking to a few people that are really focused on labs, and they said that there's been growing attention to WELL, quite a bit of interest in getting certain lab spaces certified. So I wanted to spend a bit of time talking about WELL in more detail if you're not familiar with it. It does seem to be something that's really popular in the lab space. And then I also wanted to talk about two other frameworks that have emerged, but so far WELL is seems to be the most exciting one, so that's what we're going to spend the most time on. The other two are RESET. I don't know if anyone's heard about RESET, but it does have synergies with both WELL and then the third one, which is FitWell. FitWell is very similar to WELL in a way. I'll highlight the similarities and differences as we go, and then RESET is kind of working with both in a sense. So to start with the WELL building standard, this is very similar to LEED in structure. It consists of a number of mandatory and optional design strategies that one can implement in a space. But instead of focusing on the natural environment and kind of reducing energy consumption and the impact on the environment, it's all about the occupant and enhanced occupant well-being, health, and productivity. Right now, there are two versions of the WELL building standard that you can pursue. There's version 1, this is the one on the left, and then there's the version 2 pilot on the right. And you can apply for both right now. The version 2 pilot should be matured into the formal working standard, I think sometime in early 2020, and then you won't be able to pursue version 1 anymore. But version 2 is, I would say it provides a lot more flexibility than version 1. And what's nice about it is that there's not as much kind of confusion between, well, is this type of space? Is it an office? Is it mixed? Is it this? Well, version 2 applies to all building types. So it's one set of design features tailored to whatever project you're working on, which I think it's easier for the design teams to work with. The certification process, I'm not going to spend too much time talking about this because it is really similar to LEED, but I did want to highlight two important components of it. And one is performance verification. So we often joke at our office that there's no LEED police, like no one's going to come to your project and check all of these things. But in WELL, there actually is a WELL police. They're called performance testing agents, and they do come to site to take a number of measurements, including different levels of indoor air quality pollutants. So some of those levels that we talked about earlier, which include total volatile organic compounds, as well as target volatile organic compounds, carbon monoxide, formaldehyde, ozone, and radon. The actual performance testing agent will come and take measurements in multiple locations in your building, send them to the lab for analysis, and then compare them to the air quality threshold set in the standard. So they are actually coming to take measurements and understand how your building is actually performing. And if your project doesn't achieve those indoor air quality levels, then certification is not granted. So hitting those indoor air quality targets is mandatory for any level of WELL certification. And so if you don't pass them the first time, you do have a period to kind of take remediative measures to get your building at a higher level of performance. But it is something that you will be held to. And this is kind of a key differentiator from WELL to other standards. And then another interesting component of WELL certification is that you have to recertify once every 3 years at a minimum. So if you're used to, going through certification once and getting that plaque, this is not the same for WELL. Every 3 years, you have to go through an additional round of documentation submission and performance testing, and then that is submitted for review, and then your level of certification can increase, it can decrease, it can stay the same, you can completely lose it. So you really do have to make sure your building is maintained and does perform to the level intended, which is nice for the occupants of the building because they do have that assurance that the building is providing that indoor environment that's going to have those occupant benefits. Of course, there are multiple concepts within the WELL building standard. There's more than just indoor air quality to consider when you're designing a healthy building. There's water, nourishment, light, movement, that's kind of like passive levels of fitness throughout the day, thermal comfort, sound and acoustics, materials, mind, so focused on mental health, and then community. This is kind of like creating a sense of place, like the Living Building Challenge, Pedal Intent, if you're familiar with that. But I did just want to spend a bit more time talking about the air concept of the WELL Building Standard, since indoor air quality is today's focus. To highlight some of the design features within the WELL Building Standard, we already talked about performance metrics. So this is the first feature in the WELL Building Standard, and it is mandatory, as I mentioned, that your building does have to achieve those threshold limits of different air contaminants. There are other features like including operable windows and some of those ventilation strategies we discussed. Then there are features related to filtration, so the air cleaning strategies we mentioned. Construction pollution management is a really big one. There are design requirements to protect the health of the actual workers on site, but then there are other things that would be, you would want in every building, but particularly a lab where there's, I guess depending on the type of lab, sensitive equipment and different hygrothermal, so heat, air, and moisture conditions in that space that you need to maintain. And part of the construction pollution management is things like material protection and cleaning to ensure you're not introducing any unwanted contaminants into the space, and also to ensure that the materials aren't absorbing unwanted moisture, and then installing those into a space where you could then get diffusion. Every material has a certain buffering capacity, and depending on the dynamics of the moisture conditions in the air, you don't want that moisture to migrate out and cause potential problems with like clean zones, contaminants, microbial proliferation, so like fungal growth, all of these types of things. You want a high level of control depending on the type of lab space in particular. And so the construction pollution management section has quite a few strategies that go, I would say, beyond what LEED has traditionally prescribed to help make this achievable. And I have seen this implemented, not in a lab, but in a high performance healthcare space, and it was quite successfully done. And then we have other things that are more traditional, like a smoking ban, and then maintenance and operations. This is things like filtration and change and inspection, so making sure the filters and the HVAC ductwork are replaced at at least the manufacturer specified interval. This is also things like inspection for moisture and microbial proliferation in the HVAC systems. So a lot of times, like condensate water will create unwanted moisture levels, which can lead to fungal growth. And so coils, photocatalytic oxidation, this type of thing needs to be considered and inspected regularly. And then that kind of ties into the microbe and mold control that I was mentioning. This is more of a design narrative to ensure that potential indoor sources and outdoor sources of moisture have been properly accounted for, but there also is an operational aspect where one has to go around and conduct inspections to make sure that there aren't any moisture problems, because as I mentioned, you really want those to be taken care of as soon as possible. I wanted to talk quickly now about the current landscape of the WELL Building Standard. The top bar graph, this is comparing LEED participation to WELL participation. I say participation not in terms of certification, because if you look at the databases, there are a number of projects that have registered but not fully certified. So when I say participation, I mean certification and or registration. So projects can be at different points in the series towards certification and under either of these. So with LEED, you can see that we have over 100,000 buildings participating to date. With WELL, it is so much newer to the industry that we just have over 1,600 buildings that are participating. And what that means is there's an exciting leadership opportunity for buildings to pursue this certification. I wanted to pull some Canadian and laboratory specific numbers just to show what kind of opportunity exists to kind of really define the landscape here. In Canada, we currently have, and these numbers might have changed, sorry, I say currently, I pulled these about a week or two ago, so they might have changed. They might not be exact, but they're fairly current. In Canada, we have 12 certified buildings and 52 registered. In Ontario, we have 10 certified and 19 registered. And for laboratories, as far as I could see, now I say that because some of the projects are anonymous, so there might be things that I'm not picking up in the database. there's one lab that I know of that's certified in New York City, and we'll talk about that a bit later. But especially, like if we even forget about lab-specific buildings in Ontario, even there's still quite an opportunity to be a real leader in this space, just because there are so few certified buildings, especially compared to things like LEED or BOMA. And then talking about another standard that I mentioned kind of works in parallel with WELL, and I know there are discussions with RESET, this new standard, to see how it can fit in with WELL and then fit well. But RESET is really focused on indoor air quality. And like with WELL, the performance testing is coming to the site and taking most of them, like in the next version of WELL, there's a bit more flexibility, but most of the samples are taken with sampling media. So think of like a sorbent tube and then sent to the lab for analysis. So you are collecting over a period of time, but it is about a day or two that this performance testing goes on. It's not continuous monitoring, whereas RESET is about continuous monitoring of different indoor air quality contaminants over long periods of time. And so there are trade-offs between those lab-based measurement methods versus direct read measurements due to the accuracy and resolution and the ability to detect different pollutants, like the target VOCs, for example. So right now there is a kind of a discussion going on as to what the appropriate level of accuracy and measurement approach is to really understand the indoor air pollutant concentrations and the dynamics. But this, I wanted to bring your attention to this because it's another standard that's starting to gain traction. And they define similar indoor air quality performance targets like the ones I mentioned as well. So we have fine particulate matter, PM 2.5, total volatile organic compounds, carbon dioxide, temperature and relative humidity, more comfort-based criteria, and then carbon monoxide. And they've defined different limits, what they call are acceptable. And then they also have a high performance level, which is more stringent. The high performance level here is more stringent than what WELL has set out in their mandatory air quality requirement. And so over time, it would be really interesting to see how the continuous measurements correspond to these RESET specified levels of performance, but it'll be quite challenging to achieve the high performance levels in different spaces, particularly in labs where you're often introducing new materials to conduct research, and it's much more active, is I guess what I'm trying to say, than maybe a standard office environment that I'm thinking of. And then RESET leads nicely into FitWell. FitWell is now, I would say, almost a combination of both. Initially, FitWell, I don't know if you're familiar, but it's very similar to WELL in how it's been structured. The focus, like whereas WELL focuses on the individual occupant, FitWell takes more of a, we're focused on public health in general. So some of the features in the first version extend beyond the building boundary and kind of go into community and whatnot. But it really does touch on a lot of the same components that WELL does. A bit of difference in terms of structure, like how you achieve points that leads to higher levels of certification. And I will say, like, I'm much more familiar with WELL due to my involvement on WELL projects or like the advisory board that I'm with FitWell. So for full context, I can't speak to FitWell in as much detail, but they do have a new version 2.1 that's available online. And I did want to highlight a few key changes. So in earlier versions of FitWell, there actually was no requirement to measure the indoor air quality pollutants that I mentioned with WELL. The bulk of the indoor air quality portion was writing a policy and a narrative as to how you were going to improve indoor air quality in that space. But as you can see, there are new strategies that revolve around indoor air quality testing. And FitWell does have its own set of indoor air quality performance thresholds, but there is a bit more flexibility in the pollutants that you can choose to measure. And what's also interesting is that I did notice within FitWell, you can incorporate RESET monitoring, so continuous monitoring with direct read measurements as opposed to lab-based monitoring, and that will count as a strategy under FitWell. So RESET really is working to become complementary with WELL and FitWell, which I would say are the two more design-based frameworks around indoor air quality and health and productivity in the built environment. And now I just want to close with some case studies focused on labs. And as I mentioned earlier, or at least I guess when I thought about labs and speak to kind of the design professionals that are really focused in this area, a lot of the times the discussion is about safety and fume hood design and kind of isolation to prevent unsafe working conditions. But it's also starting to go beyond that now, I've noticed. People really are focused on creating productive work environments where really leading scientific research can take place as optimally as possible. So I'm going to start with a case study that combines indoor air quality with more of the traditional approach. I say traditional, you might disagree with me, but I guess what I think is the more traditional approach of designing for safe conditions in a lab space with also energy efficiency in mind. And then we're going to highlight a few examples where attention has been put towards really enhancing the space as a great place to work. So to start, this is some archetype modeling, energy modeling, that our energy modeling team here at RWDI conducted for an education institution. And they took a number of typical building types, so you can think academic office, heritage building, and laboratory research building, to understand how different energy conservation measures, or ECMs, if I accidentally referred to them as that, have an impact on the overall performance. So these bar graphs are for the laboratory archetype model. And we looked at different things like the amount of exterior wall insulation. You can see for each there's a baseline, and then there's kind of a reduction in performance and then an increased performance. The same goes for the infiltration rate, the occupancy hours, and then the lab ventilation requirements. And if you look at the magnitude of the difference between the resulting energy performances, the lab ventilation requirements had the largest change, from a drop in 23.7% from the baseline to an increase in 17.2% from the baseline in the positive direction. And so what this archetype modeling study showed was that really ventilation appeared to be the driving factor for the laboratory energy performance, which is often challenging because, as I mentioned, we want to design for safe conditions. And if there are certain like fume hood exhaust rates or other air change rates that have to be met to achieve those conditions, then there isn't too much flexibility there. But I'm going to introduce this briefly. I know in the annual schedule there is an air acuity specific presentation, so I'm not going to go into too much detail. I'll save it for the full hour devoted to that. But wanted to mention a dynamic ventilation approach and the resulting energy achievement for this project in particular. I can't say which organization or facility it was, but basically they were looking at implementing demand controlled ventilation with the air acuity system. So basically installing a number of sensors within the facility to measure the concentration of different indoor pollutants at these different areas. And essentially what this does is by measuring the air that is sent to these sensors, they can understand when there is a spill or kind of an accident scenario where there's a higher concentration of one of these contaminants that needs to be diluted. So instead of always operating at a higher air change rate, they can reduce the air change rate to a lower level, say like 4, during normal conditions, and then increase it depending on what's occurring in that space. So this is a graph, and my apologies if you've seen this before. This is a graph that shows a spill scenario, and you can see the concentration increasing of this certain contaminant over time. And then the blue is the baseline scenario where there's no dynamic ventilation strategy in place, so just 6 air changes per hour. And then yellow is the dynamic scenario where we're going from 4 air changes per hour to 16. And what I want to draw your attention to is, like, let's look at the difference in the peak concentration between the dynamic scenario and the baseline static scenario. So there's a much lower peak concentration achieved in the dynamic scenario. And then when we're looking at the target indoor air concentration that we want to maintain this contaminant at, so about 250 parts per million, you can see that the dynamic scenario is able to achieve or hit that threshold earlier in time than the standard non-dynamic scenario. And then, so there's benefits from a health perspective, both in terms of the peak concentration and the duration of time that we have exceeded the recommended threshold. But in terms of energy as well, the estimated energy improvements for this project are quite high. We have a reduction in electricity consumption over the year, just over 200,000 kilowatt hours. And then we also have quite a big reduction in natural gas, equating to reductions in both Scope 1 and Scope 2 greenhouse gas emissions. Scope 1 and Scope 2 quantified separately just for the nature of this project, but I will also say these are just estimates and the project isn't fully online yet, so we'll have to see how it actually performs. But that information is coming soon and it'll be quite interesting. Whoops, sorry. And then drawing our attention away from the more traditional kind of safety, spill, and energy design considerations, now I just want to close by highlighting a few examples where we really took attention towards designing for the occupant. There are a number of ways you can go about doing this. You can start by achieving formal certification or just shadowing formal certification. But one thing we've seen people really interested in is understanding what the actual baseline conditions are in their space. So here we have a graph on the left of temporal VOC concentration in a workspace. So we measured the volatile organic compound concentration over a period of several weeks. And then we plotted this against the well performance target, and you can see that we've exceeded it over quite a long period of time. And so this office space is now working to implement different strategies to reduce that concentration, and they're holding off on pursuing well certification at this time just because they know it would likely be infeasible until we can reduce this concentration down. There are different options available to do this measurement. You can do the high accuracy lab-based approach. So this is an image of some sorbent tubes where you could collect samples in the space and then send them to the lab for analysis. Or if you want to do a less accurate, longer period of measurement, you can pick a direct read sensor. This one I would say is quite accurate. This is an AirQual Series 500 monitor, but you can get lower cost sensors if you are more interested in a ballpark range. You can even, I know like I track my exposure to particulate matter when I walk to and from work. So you can do this type of stuff. Like if you're interested in understanding how your different indoor environment is performing, you can get different grades of sensors available to help contextualize that for you. And then moving beyond kind of like these feasibility studies, you can then pursue formal certifications. So as I mentioned, we do now have a lab that is well certified. It's well certified gold in New York City. It's the Alexandria Launch Labs. Seems to be quite pharmaceutical based, but I wanted to highlight a few features. So obviously, number one, to achieve well certification, they would have had to meet those indoor air quality performance targets, but they also went beyond the thresholds for particulate matter, organic gases, inorganic acids, radon, and oh, sorry, I forgot to mention that as part of well version 2, you do have to measure indoor air quality, I believe at least once a year, but not to the same level as the performance testing. And it's not nearly as frequent as and continuous as the reset requirement. But sorry, I forgot to mention that one. So they did meet the fundamental air quality requirements, but then they also did go well beyond that to achieve the gold level of certification. And this is even beyond the lab space itself. So within the facility, they do have a fitness center that the occupants are free to use. And then even nearby, they have an urban agriculture center where occupants can take breaks, do some gardening, and just like have more access to nature. And all of this, I know it may not seem like this is relevant to a lab space, but all of this does really improve the occupant performance. Like when you exercise, that's going to improve your focus in the lab environment, either immediately, depending on the time of day you exercised, or the next day. And then access to nature has really, there's been demonstrated reductions in certain physiological markers that show stress, lack of focus, and anxiety in these types of things. So I'm really all for these design strategies, and I know sometimes it might not seem to certain design teams relevant to be talking about these things, or perhaps that allowing your occupants or your employees to take a break to go to the gym or the garden would be productive, but there really is scientific evidence that these are proven strategies for improving occupant health and well-being, but really productivity and the work that's being conducted in the space. And I think we have a bit of time for questions. I hope this was informative. I know it's still kind of an emerging topic and might not be super familiar. So if you don't have immediate questions, feel free to jot down my email address. And I'm more than happy to take questions over email, or we can even set up a call if there's something in particular you'd like to discuss.
Great, thanks, Sandra. That was very interesting. It looks like there's a little ways to go before well becomes really, I guess, a standard in Canada and elsewhere. But it seems like it's on its way.
Yeah, I feel like it's really starting to get there. It's been slow going. One thing I did forget to mention is with version 2, the fees associated with achieving certification have really dropped, and I know that was such a barrier for version 1. Like the fees were so high, it was kind of a conversation stopper.
Yeah, let's see if we have any questions here. Do you have one? Can you elaborate on the reset system and how it relates to WELL certification?
Oh yeah, sorry, I didn't do the most clear job of that, but right now the founder and lead in charge of developing the reset standard is really working to harmonize with the WELL building standard and kind of understanding how the two can work together. So similar to how reset has become a feature within Fitwell, they're looking to do the same thing for WELL. I know I've been involved in some of the discussions there, and right now the main challenge is agreeing on the accuracy levels. So WELL requires much more accurate methods of measurement, whereas reset is more relaxed in the accuracy and resolution of the devices, but that makes them more accessible. So I think where we're stuck right now is there's this debate between, well, if it's too difficult to measure, people aren't going to want to measure it, but if it's not accurate enough, is the data even meaningful? So that's the main question everyone's trying to sort out now, is can we get to a level of accuracy and accessibility that is appropriate for both? But you are still free to pursue both individually.
Okay. Another question. Have you installed Aircuity in lab spaces, and how effective do you believe it is? Not sure.
Myself personally, no. And then I know it's been quite popularly used in a lot of lab projects our company has worked on. The only one that I have the estimates for is the one I showed earlier. And as I mentioned, those were the design estimates. The project isn't fully online yet, but come say the fall this year, we should have a better idea of how it's actually performing. I know it's a really interesting concept, but I know it's more complicated than just increasing the air change rate and decreasing under the measured conditions. Like I know there's air mixing, and the fact that air change is more like air exchange. It's not a complete swap of the volume. It's just a certain quantity of volume of air that's being replaced. So I know the modeled results and the energy modeled results that we have for this design might not be realized in once it's constructed in operation, but I can't speak from personal experience to kind of the level of effectiveness. But that sounds like the Aircuity webinar would be the right place to kind of discuss that further.
Yeah, I think so. Another question, does RWDI often get involved in lab risk assessments related to setting target air change rates for operations and evening setbacks, etc.?
Again, I couldn't speak to that just from my personal work, but I believe there's someone here. If you want to send me an email, someone could speak to that in far more detail. I believe that's more their area of specialty here at RWDI. So if you send me an email, I can put you two in contact.
Okay, another question related to Aircuity. It looks like, what alternatives are available for Aircuity?
For a specific, I'm assuming that's like a specific measurement-based demand-controlled ventilation scheme. And I haven't seen one myself, and I've spoken to my colleagues about this as well. I haven't seen a similar alternative for a measurement-based demand-controlled ventilation strategy for a laboratory environment.
Okay, well, that looks like all the questions for now. I would, again, invite everyone to jot down Sandra's email address. If something comes up afterwards, please feel free to reach out, and I'm sure she'll do her best to get back to you.
Yeah, please do. I'd be more than happy to answer any additional questions.
And Sandra, I guess just on behalf of all of us, I'd say thanks for the presentation, but even a bigger thanks for getting involved in WELL and trying to make a difference, and we appreciate that.
Oh, thanks. Yeah, I'm really excited people are enthusiastic about it. I think it's really important, and I hope it gets as much attention one day as energy efficiency.
Yeah, I think it will. I think there's a much greater awareness out there these days of the impact of. We've all seen people falling asleep in afternoon meetings, so
Yeah.
I think there's a general awareness that it does matter.
Yeah, I would agree. No, it's great. Yeah, and thanks everyone for attending. I really appreciate it.
Okay. Well, we'll let you go for now, and again, thank you.
Great. Thanks. Have a nice day, everyone.
Yeah. Bye now.